right.
All right, okay. So again, good afternoon, everyone. We'll continue with the class today talking about stresses and pore pressure. I just wanted to give you an idea about where we are. We already went through the introduction. You are solving homework number 1, which is due on Friday. And now we're getting into chapter number 2. And we're going to try to finish all about stresses and non-hydrostatic pore pressure, and Wednesday, ideally, we'll start talking about horizontal stresses. So that's where we are going. All right. Before I start, I wanted to show you a video. Let me lower the Look at the octopus. This is the seafloor, right? And the octopus is probably escaping from some other animal. It just digs in and gets into the sand. I don't know exactly what is the depth at that location and what is the pressure in there, but let me play it again. But these are very similar conditions to the ones that we may have in any other location at the seafloor. As I told you before, the sand is not locked in by anything. You can move it, that's the way the octopus does it. And in this location, something that we have got to know recently, which is effective stress, is nearly 0. There is one more thing which is very interesting that the octopus does. I want to see it one more time, okay? When the octopus wants to get in, blows water into it. You see how it's pumping water? So by increasing the pore pressure, lowers effective stress and makes it like quicksand. Quicksand is basically a sand in which you don't have any effective stress. If there is no effective stress, there are little forces, very small forces between the particles, and it's very easy to move. When effective stresses are very high, and that's something we're going to see later on, even an unconsolidated sand can get pretty hard to deform and to break. So that's when we come back over here and and now we'll continue talking about stresses. So we talked about pore pressure, and we said that pore pressure is about increases about 10 MPa per kilometer in SI units, or about 0.43, 0.44 psi per foot. We also talked about total vertical stress in these onshore conditions. We calculated that the bulk mass density of rock is about 2,320 kilograms per meter cubed. Let me ask you, with this bulk mass density, what's going to be the gradient of total vertical stress? The gradient of pore pressure, let's do it first in this metric unit. If the pore pressure gradient is 10 MPa per kilometer, and this one is 2.32 times bigger than the density of water, what do you think is going to be the gradient of vertical stress? Anyone can tell me what is going to be?
23.
So, remember the density of water is 1,000 kilograms per meter cubed. So this one is going to be more or less, with that number, 23 MPa per kilometer. is just 2.3 times bigger than that one. That's a variation of vertical stress with depth. If, for example, you were at a location which is 2 kilometers deep, the vertical stress with this bulk density would be 46 megapascals. Okay, this was the case onshore, and in a few minutes we'll solve the problem, but I'd like to finish with the case offshore that we started last week, and we presented conditions here at the seafloor for that octopus, so we're trying to get it. All right, so now our objective is to calculate vertical stress and effective vertical stress with depth, but it's not the same as what we had before. Pore pressure is, if we assume it's hydrostatic, it's still connected, the pore space connected towards this free surface, it's going to be the same as before. Density of water times G times depth. Vertical stress is going to be the same as before, but there is a small difference. And the difference is that the bulk density is not the same as if you were in water or if you are in the rock pore space. So that's going to change our numbers. In offshore conditions, the vertical stress, notice that there is a kink over there, and we're going to introduce one additional variable here, which we're going to call the depth of water. SV is going to be equal to the density of water times G times the depth of the water, plus, if we assume all this density is the same, the bulk density of the rock times G times the actual depth minus the depth of water. It's very important here that you notice that the depth starts at the sea level. It doesn't start at the seafloor. We could also write our equation so that they start at the seafloor, but we're going to see later on that it's much more convenient for that depth to start at the sea level. So now if you want to compute your total stress onshore, always remember to add the weight of the water, which is on top of the sediments, for which you may want to calculate wellbore stability or pore pressure or effective stress or any other quantity that you want to work with. Yes?
Is the difference in density bulk, like you said, it's not going to be the same as you go down? Is it significant enough to make a big difference, or assuming that it's constant is just a rule of thumb?
We are assuming right now constant to make it a little bit easier to deal with, but the next step is to make this one, which is not constant. Actually, you raised a good point here. I was forgetting one plot. Let me move this one over here. And here I'm going to plot the bulk density as a function of depth. We are assuming that the density of water remains the same with depth, and the bulk mass density is bigger than the density of water. When you're in water, of course, the bulk density is the same as the one of water. In reality, there is not such a sharp transition here. The density of the sediments starts to increase slowly with depth. More burial, more stresses, lower the porosity of the rocks and make it heavier. And we're gonna get there in a minute, but for now, let's just assume this as constant. Okay? So, vertical stress onshore simply is going to be the lithostatic gradient times depth. And if you do it offshore, remember to add always the weight of the water, and then it will multiply the density of the entire rock times G times this difference in depth, and you will get a vertical stress. Okay? So let's work on two problems very quickly. And these are going to be let me come over here. Okay, we already solved this one in class. I didn't go in detail into that, but just take a look, try to solve it on your own. In the homework there is a very similar one. And it's what I just showed before. We're going to talk about this coffee example later on. And this is the one I want you to solve right now, okay? I'm going to make it a little bigger so you can read. I'd like that you compute the vertical stress at 4,000 feet of depth in a place onshore, but notice now the brine density is a little bit heavier than 1 gram per centimeter cube. And you also here have the rock bulk mass density. So, as you start working on this problem, I'd like that you remember very well 4 numbers. And they're easy to remember. Let me switch quickly over here. Hydrostatic pore pressure gradient. What did we say is that value? How many psi per foot? Let's say 0.44. If you do 0.43, I won't complain, okay? So 0.44 psi per foot. I like that you remember that number very well. And this is the same, we said, to 10 MPa per kilometer. Total vertical stress gradient. Also called sometimes lithostatic gradient. Let me write it over here. Lithostatic gradient. That's going to be, we found the value in metric units, which is 23 MPa per kilometer, right? And if this is 23, how much is this number going to be? Can anyone use the calculator and tell me how much that's going to be? Actually, it's going to be a very easy number that it's almost impossible to forget.
It's 1 psi.
How much? 1.102, right? So let's say 1. Let's round it, 1 psi per foot. That's increase of total vertical stress with depth. For these numbers, I have assumed a density of more or less 1,000 kilograms per per meter cube. For this one, I have assumed a density of 2320 kilograms per meter cube. Per meter cube. So if you have a brine heavier, you just have to multiply it by a number, by a scale number that would make this number heavier. Let's say this is, you have a brine which is 1100 kilograms per meter cube. Then just multiply this number, if you want it, on field units times 1.1, and you will get your gradient. If you got a rock which is 2500 kilograms per meter cube, divide 2500 divided this number, and that's your proportionality number to which you will multiply any of these two numbers, and you will get immediately the gradient. Okay? So remember, lithostatic gradient, 1 psi per foot or 23 MPa per kilometer, hydrostatic gradient, 0.44 psi per foot or 10 MPa per kilometer. Now let's come back over here and you can solve the problem. For now, let's just solve it in field units, okay? Don't worry about the metric units because the problem starts with feet. So you're going to have to convert those densities, as we discussed before. You're going to have to convert them to gradients. You multiply the gradient times depth, and you get your value of pore pressure or stress. So work on that and let me know if you have any questions when I try to figure this microphone how it works. Any questions? Okay, now it's working.